Thanks, Anupam, for your elaborate introduction. Uh, so this is the first time, of course, I'm visiting this campus. Such a beautiful, compact campus. It's small but very beautiful. Thanks for inviting me. So I'm getting to today's topic. I was told that except chemist, everybody is there in this campus. So that makes my job very interesting. So I'll try to put things as general as possible, but stop me whenever you want. So let me get going. So the title I kept is the Mimicking Transition Metals During Catalysis. Let me first tell that this is the topic we are developing last 10 years in our laboratory at ICTS Kolkata. So let me tell you why this particular topic is important. So that's very important to know why mimicking transition metals are important in catalysis in particular. So let me start with a very old and very well-known process called Haber-Bosch process. In fact, catalysis is something very important which directly contributes to the growth of a country, developing country, about 20 to 30%. It's such an important process. And I'm bringing the example of Haber-Bosch process because this is one of the oldest process, industrially important process, which was discovered in collaboration with Haber and Bosch from BASF in Germany, which actually did fixation of nitrogen and then conversion of nitrogen to ammonia. And then this ammonia is used for making a lot of fertilizers. So it is now not just exaggeration, but the fact. In our tissue, the 50% of nitrogen comes directly from the Haber-Bosch process. It's such an impactful catalytic discovery in the century. In fact, 400 million tons of ammonia is synthesized, fertilizers are synthesized, and it is called that 2/3 of people are being fed by this only one process. Now, why I'm bringing this process? Such a huge industrial scale, Haber-Bosch process started with using metal like osmium or uranium. The first discovery when Haber-Bosch discovered the process, they used uranium and osmium. However, they soon realized that this osmium or uranium, they're very, very expensive and they're rare. And right now, Haber-Bosch process runs for more earth-abundant catalyst, iron-based catalyst. Okay. So this was something realized for long back, like more than 100 years. So people thought of starting with very expensive metal, then to develop something of industrial scale, you have to come to a very earth-abundant, which is more cheaper metal. And right now, iron is used as a metal-based catalyst. So this is a problem. Now we are trying to do little more ahead actually. So can you design a catalyst which even go further? You don't need to use even transition metals. Iron is still transitional. Okay. So that is our major goal. How can you actually design your catalyst for different processes which could be industrially or medicinally important, and then you don't have to use metal. Now you can ask me that what's the problem with metal? I mean, if you use metal, then why? What are the difficulties or disturbance? Now, I will just show you a table. This is something I took it from Google or literature, you can tell. You know, these are the metals: gold, platinum, palladium, ruthenium, iridium, and rhodium. They are very exhaustively used in different industrial processes. But I would like to remind or emphasize the fact that if you look at the abundance, the natural abundance of these particular metals, which are very frequently used for different industrial processes, you look at they're actually rare metals. And it's no wonder that the price is given in US dollar, also in INR per kilogram. is hugely expensive, right? Now, so question is that, so can you make replacement of these metals which are rare and expensive with metals which are actually earth abundant, which is called earth abundant metal? If you look at the abundance, is quite huge, and as a result, the price is of course very low. So can you change all those heavy transition metals which are rare, expensive, and then exchange with these earth abundant metals? So that was one of the global issues that people have tried to do that. Not only expenses, but also, it's about toxicity. For example, if you use too much platinum, that platinum is very bad so for tissues, and it can cause platinum poisoning, or heavy metal poisoning can happen with different types of heavy metals. Now we are talking about actually not in gram scale. When you are talking about industry, they are being used in kilogram, in ton scale every year. So it comes back to the environment, right? So this is a global concern. How do you avoid such expensive and toxic metals to use? So in my talk, what I'm going to try is to show you 2-3 reactions actually, and they're typically known to take place with the help of transition metals, and then how can we design our catalyst principle so that we can avoid these kind of transition metals. Let me take you through a Nobel Prize which is more than a decade ago, not more than decades, just roughly a decade ago, 2010. This Nobel Prize was awarded with 3 scientists, Suzuki, Heck, and Negeshi. What they did is basically they showed how to form C-C bond, carbon-carbon bond. Okay. Now they have shown 3 reactions. This is called Suzuki reaction. This is called Heck reaction. This is called Negeshi reaction. Okay, so ultimately what you see is basically in the blue and red, they are coupling through a carbon-carbon bond, blue partner and red partner, and there are different types of carbon-carbon bond forming reactions they discovered. And all these catalysts were done with the palladium catalyst. So other than palladium, so all 3 scientists they discovered the use of palladium catalyst in doing this CC coupling catalysis. And in recognition, it was the Nobel Prize was received, but soon after Nobel Prize, so let me tell you why this Nobel Prize is so important, in terms of industry. So this is the basis of a lot of billion-dollar molecule synthesis, this CC bond coupling reaction. For example, if you see that telmisartan, which is used daily as an anti-hypertensive drug, even Dr. Reddy sells as Telma, right? So this is the CC bond, this red color. So this is forming with the help of palladium-based catalyst. Okay, paclitaxel. This is another blockbuster drug which is used for chemotherapy for variety of cancer, and this is again another blockbuster drug. Once again, it is done through a Heck-type coupling. This red bond is formed with the palladium catalysis. And examples are a lot. I just taken few. This is a hepatitis C virus. Once again, this bond is formed by doing the CC coupling catalysis. Now, not only in medicine but also in the area of agrochemicals, this is the fungicide Boscalid marketed by BSF. This is another multi-billion-dollar drug. And of course, you can see that PPV, which is used in your TV screen, is also used through this type of CC coupling catalysis. Okay. Now, let me tell you all these things, they have utilized palladium. And this is something little more technical slides. So I would like to now criticize the Nobel Prize in 2010 and how the modification started coming last 10 years. So the moment, this was the Nobel Prize, Nobel winning reaction in 2010, where this blue and red partner, both partners, when you couple, you have to do certain chemical synthesis before you take them for coupling. This is called chemical modification. And each step in the industry requires a lot of manpower, a lot of energy, and it's a cost, non-cost efficient process. Okay. Right. So now the modification started that the first question was asked, can one of these partners be used as such that you don't need any modification? So if X is some chemical functionality, if X becomes hydrogen, then you can do a direct cross coupling. This is a traditional coupling, right? So if both the partners need modification, at least you can avoid modification, chemical modification of one partner, so that another partner still be modified, but they can be coupled. So it's called direct cross coupling. This is something called CH functionalization process. So you can cut down your cost a lot if you can do that. Now, yes.
Is X a halogen?
I'm sorry.
That X.
Right. I kept it more normal. X could be right. In this case, X is halogen. One of the partners, yes, X is halogen.
So one needs to modify Y into a halogen to do this, right?
Actually, there is a drawing problem. So this X, I kept it. This is something. It was my mistake. Actually, it should have been blue colored X and with hydrogen, and this should be Y. Actually, it doesn't matter, but this is some technical mistake in the drawing. But what I'm trying to tell is that one partner you have to modify now. You don't have to do modification in another partner where you can do CH functionalization. This is called CH functionalization. Now, if you go further, you can do in such a way, both the partners you don't have to modify, do the two hydrogen CH. This is more difficult, thermodynamically more uphill process you can do. This is called dehydrogenated cross coupling. So all these are modifications in the last 10 years. But once again, I have to tell you, all this modification was successful only with the help of palladium. Okay. Without palladium, it was not kind of known. Okay, so now this is something I would like to tell you. So the point I'm trying to tell you, if you want to do CC coupling catalysis, you need, palladium. And palladium, if you look at this, this is used 16.5 metric tons, this much kg palladium we use every year, and you can see that it is as expensive as gold, right? And this is very, very rare metal. So basically destabilizing whole world if you keep using such an amount of palladium for doing all sort of reactions, right? So this is a global concern, and
catalyst to get back after the end of the reaction. Right?
I'm sorry.
Catalyst is not consumed. Doesn't not get it back after that.
Well, I mean, many. If you are making a heterogeneous catalyst, you can get back, but in a homogeneous catalyst, it goes. So you cannot recover. Most of the pharma industry is standing on the homogeneous catalytic process, but material science once again is mostly on the heterogeneous. Because pharma, you have to make certain, inertial selective synthesis. You can't do heterogeneous chemical process. Okay, this has to be more mild condition. Okay. Right, and you cannot recover everything basically. So the question we try to ask is quite difficult. So if you can do with this whole process, CC coupling process, without transition metals. So that's the question we try to ask. Now, if you really want to do that, you need to go back to your catalyst design principle, your drawing board, your fundamentals, how the catalyst is designed. Okay, right. So if you look at the catalyst design principle, you can see that catalyst designs could be either based on Lewis acidity. Lewis acidity means what I'm talking about. It can accept electron. Your substrate can be activated by transfer of some certain kind of charge transfer from the substrates. So a catalyst accepts electron and then it can do the Lewis acidic activation. Or it could be redox activity. That is the typical point of transition metal. Redox activity means it can transfer electron, then gain back electron during the catalytic process. I will just show you how it does. So either it has to be Lewis acidic, or it could be redox active, or it could be Lewis basicic. Right, so these are the major three principles most of the catalysts are done. So Lewis basicity is something like that, so you have a lone pair of electrons, you can transfer the electron. Catalyst will give electron and then activate the substrate. Okay, so it's opposite to the Lewis acidity, of course. Right, so I will now tell you two reactions actually, how we have designed, which is typically done through transition metals. One is the carbon dioxide reduction and one is the CC coupling catalysis. That's what I want to show you how to do without transition metal. Now, this is a Lewis based. I would like to introduce, don't bother about such a big structure and all. But pay attention to this lone pair actually. So this is a carbon, tetravalent carbon. So we are using bivalent carbon here. So this is a carbene, it's called carbene. Now this carbon is having bivalency and then it will have a lone pair of electron, so that this lone pair of electron can attack to the metal. Okay. Now this is something we call as a N-heterocyclic carbene. This is a technical name. So this can give the electron density to the metal, and this is a new version of N-heterocyclic carbene which was reported in 2009. Before that, there was an old version of carbene, which is again is known as normal carbene actually. So this is called Drawbacks catalyst, where this carbene center is between two nitrogen. Here actually carbene center is between nitrogen and carbon. Okay. So this is called abnormal carbene and this is called normal carbene. Okay, but the point is that these carbenes are good to bind with the metal, and they have a lone pair of electron, and they stabilize catalyst, and they are very good in designing catalyst. That is the basis of Nobel Prize in 2010 by Drawbacks, because this is a very important catalyst for doing something called olefin metathesis. Okay. Now this is a newer version of carbene, which can be used as a Lewis base, but very highly energetic, means highly unstable carbene actually. So we used this carbene. So this is 2009 reported. Now once this carbene was reported, there are a variety of groups started working. Drawbacks himself, who is the Nobel Prize winner 2005 in normal carbene, he started working on various chemistry, like ion-based chemistry he developed. And then, what I'm trying to show you that across globally, this is from Germany University et al. Developed germanium-based chemistry, and this is from again Germany. They used carbene boron-based chemistry, and this is gold-based chemistry reported in 2018. So the point I'm trying to tell, this carbene, this is a new version of carbene. Across globally, people started utilizing this, but nobody actually used this in designing catalyst. Okay. So what we started so at the same time, we started developing a lot of carbene-based chemistry in our lab. In fact, we reported the first catalysis out of this carbene. So we developed a lot of heavy metal chemistry. That was something we developed, but which are not, of course, not today's topic. And then we used lighter metal chemistry, main group chemistry, and this is something I will be talking a little more. And how to do metal-free CO2 activation using this particular carbene. So you don't have to use any metal, but use this very highly reactive species and then capture carbon dioxide and do the activation. So whole idea here is that, so you design a catalyst which can capture carbon dioxide, okay, and then hold carbon dioxide, put some reducing agent, then you can convert carbon dioxide to methanol. So, and then fuel, that methanol can be used as fuel, and then you burn fuel, you can get carbon dioxide. So it's a cycle that carbon dioxide can be captured and then converted. Of course, these are all talking about laboratory scale, not industrial scale. Now, why do we use this particular carbene is the following. So if you look at the original calculation that was published in this paper, which shows that the normal carbene, which was used by Drawbacks, actually homo energy level of this particular carbene. This is a highly energetic, high energy orbital contains this lone pair of electron. If you do the comparison, and thus the nucleophilicity of this particular carbene is very high, so it can capture carbon dioxide molecule by a reaction where C of CO group can be attacked. That was the idea because of the high energy orbital presence in this carbene. So with this idea, we started using this free carbene, and then we used carbon dioxide from cylinder, and then we saw this carbon dioxide could be captured with this carbene. It forms an adder, and this CO2 adder can be captured at room temperature at atmospheric pressure of carbon dioxide. Generally, even metal-based catalyst requires high pressure of carbon dioxide. This is an ambient condition. We could capture carbon dioxide. And once the carbon dioxide is captured, then you put a boron hydride, that's the reducing agent. So you can transfer electron, the hydride, and then it can get you boron methoxide, which you can do water hydrolysis. Then this hydrolysis you do, you can get methanol, and then methanol is fuel. Right, so what we did in the process, we tried to understand how this mechanistic cycle is going on, and then we did some sort of control reaction by which we treated carbene and boron in presence of CO2, and then we trapped one intermediate and crystallographically characterized just to show that how the carbon dioxide gets inserted and captured in the boron molecule. And this is an active intermediate of whole mechanistic process, and this itself can be a very effective catalyst. You can see that PON is something called turnover number, which shows how efficient your catalyst is. In fact, we reported this compound in 2016. That time it was the best known catalyst under homogeneous condition. This was giving 6,000 PON value, which is kind of way higher than that of earlier report. Earlier reported was 1,800. Okay, so it is a big improvement by using such a very highly reactive carbene. Of course, I have to tell you that this carbene is a big pain to synthesize and store. So you have to store this carbene inside a glove box, nitrogen-filled glove box, inside a refrigerator, which is stored at -20. So sometimes it's very frustrating to work such an unstable species, and do catalysis with that, because anytime glove box goes bad, carbene will go bad immediately. So you cannot store it for a long time, more than 2 weeks. You cannot store. Every time you have to prepare. But even then, such a reactivity is actually boon to us, because this is such high reactivity can capture inert gas like CO2 because of the high reactivity. Well, so then we took a more challenge actually. So far I was talking about CO2 capture from cylinder. So you have a pure cylinder and then transfer to the rubidium and then you capture. Now the next question we tried to ask, can you do the same reaction, CO2 taking from air? Because that's more and more practical, right? But the problem is that CO2 in air is very less, right? It's 400 ppm. So you have to be very, very selective if you want to do that. But this could be very practical, because there are several companies we know that they're working for CO2 capture from air. This is a company established by David King, which is established in Canada. So they are trying to do an industrial scale CO2 capture and conversion to methanol. Okay. Now what we showed in our work, such a reactive carbene can do reaction with boron, and then they can form a Lewis acid pair, acid-base adder, and then we can do the X-ray crystallography to see the structure. And then once you keep this carbene boron adder, this is a yellow color solution, on air, you expose, and then you see a color change, soft color change from yellow to green, and then you see then slowly you blow crystal, and you see that CO2 is trapped from air. So we are very delighted to notice that CO2 can be trapped selectively from air and from a low concentrated source, and then it's a format. And then you take this format, you can put a boron hydride, you can convert boron methoxide, which you can hydrolyze to methanol. So basically you can convert air, the CO2 from air to fuel. And then this is also, once again, you can do not only fuel, but also fine chemicals. You can take the CO2 to formic acid. However, I would like to tell you drawback of this reaction. Actually, this is good to hear that we could do the CO2 conversion from air to fuel and fine chemicals, but we could not make this whole process catalytic. This is all stoichiometry. Okay, if we can do catalytic, this will be huge. We are trying for that actually at this moment. And then very recently this got accepted in journal. And by the way, so let me tell you the fact that so far I was actually talking not about my topic. Okay, I was talking how to avoid transition metals in doing CO2 capture like reaction, which is basically dominated by transition metal based catalyst. I talked about how to avoid transition metal, but this is not mimicking. This is not a typical transition metal works during the catalysis. Okay, so so that's why I wrote here it does not mimic transition metal. So if you want to mimic transition metals,
I have a question.
yes.
So you described this capture of CO2 from the air
Yeah.
in the previous slide. Is that what is and you converted it into a fuel? Is that what you said?
Right, yes.
So is that what is the net energy or exergy input you have to do to get this? I mean, it seems.
Well, I mean, so this is all done at room temperature. Okay. I'm sorry, so what's your question? Once again, so
There
net
is a
energy
you
of
can convert something into a fuel
right.
without putting in. I mean, what's the thermodynamics of this whole?
Yeah. At this moment, I can't give you a number actually. So we have done a full calculation of this whole process. So every step, we have done the calculation and activation energy and all these things.
So the full life cycle.
Right, full cycle actually. So that's
the net should be negative, right? I mean, you have to put in more. I mean, are you using some sort of fuel to do the reaction?
No. So this is, I mean, we are being captured, and so I should have kept the mechanism. So I did not keep it. Maybe we can talk it more details because we know how exactly happening every steps of this reaction. Maybe that will clarify more actually. I have a paper.
Is this something that
So what it does is basically once this is forming, then BH bond gets activated. There is an insertion mechanism happening inside the BH bond or CO2 molecule actually. And then the activation energy barrier and all these things have been calculated in the paper actually.
Right, but without knowing the details, I mean, the question is more about the net thermodynamics of the whole process.
Yeah.
So I'm just wondering, because you convert something that is like CO2, which is floating around in the air, into something which can be used to do work. That's a very naive question. So
Whether one can build a perpetual machine.
it sounds like, it seems like there must be something somewhere, some input.
Yeah, maybe we can discuss about the calculation and numbers actually. So it was there some mechanistic cycle because I thought that I'll make it more general, so I just took out.
Okay, and
so
maybe related to some more general question is like you're capturing CO2 from there. There's this big attempt to capture CO2 on a large scale from the air to reduce the effect of greenhouse gases. Is this type of reaction something that we can implement for large scale at the geo engineering level to capture?
Right. So this is something we have not done so far. It's just milligram. I mean, microliter scale.
But I'm asking potentially, is it
so
something?
potential is there. So what we have to do is actually, in fact, I span off a company out of this. You might have noticed that I have attended this technology. So in fact, we are trying to develop the heterogeneous version actually. So you have to go for kg scale. Okay. And I mean, so when you convert a homogeneous process to heterogeneous, it's a big challenge, I mean. So,
I don't know what this
so I don't know, I also don't know whether it will work or not in the large scale, but we are on it actually. So,
What is heterogeneous?
Heterogeneous, I'm sorry, what is the question?
What is the difference between homogeneous?
Oh, I see. So homogeneous and heterogeneous, I mean, so when you're all catalyst, reagents, everything goes in solution actually. They're in same phase. And homogeneous is that you don't have same phase. Okay, so your catalyst will remain insoluble so that your separation after the catalytic process will be more easier. So you just do a simple filtration, you can take out the catalyst. And homogeneous, you can't separate after the reaction. So you cannot reuse. So any industry of this kind of process has to be heterogeneous. So this is not a true model for doing the industry scale. I have to first heterogenize. Means I have to fix the catalyst on a surface of a substrate, let's say graphene it could be, graphene oxide it could be. Then fix it, so it will never go in the solution, so your catalyst can be recycled again and again without loss. So it's very effective. Okay. Now, let me put, if you want to do mimicking transition metals, I'll take you an example from the textbook actually. So when we teach a course on organometallic chemistry, so this is one of the major pathway we discuss about. This is the Nobel winning pathway 2010 Suzuki reaction. Okay. So look very closely. This is the palladium which is catalyst, as I told in the beginning. So this is a palladium 0 is used as catalyst. Okay. Now what it does, the first step, as X is equal to, you mentioned that it's a halide, this is an alkyl or aryl halide. So it goes as something called oxidative addition reaction. What metal does basically, it undergoes an oxidation from 0 to +2 oxidation. So that means metal transfers 2 electrons to Rx bond and it breaks, it tears it apart. And then you get R and X broken. So you get this species where palladium is 2. The first step is called oxidative addition because there is an addition and there is an oxidation of metal. The second step in this Suzuki coupling reaction, this is one partner of your coupling and then another partner comes closer. So this is a coupling, it's like marriage, right? So this is a catalyst which brings both the partners together, R and phenyl, and now this is called something called transmetallation process where the another partner comes close. But here you see palladium 2 does not change any oxidation state. It remains palladium 2. And then last step is the called reductive elimination where these two partners forms the bond and then palladium 2 goes back to 0. That's called reductive elimination because there is an elimination and there is a reduction of metal because the electron is gained back by the palladium 2. Okay. So this is something that can be looked upon something like this. This is a very interesting proposal came up in 2014, which talks that the role of a catalyst is nothing but supply of electron. So this step, you can see that the catalyst is basically electron, which is lost during this process to form this product. This is just this version. I'm just looking at different way. Now this 2 electron is lost, then there is no electron transfer or electron exchange in this process, and then finally you gain back the 2 electron because of the reductive elimination. So they proposed a process where electron is actually acting as a catalyst. So what is the role of metal? Metal's role is transfer electron at right potential to the substrate's antibonding orbital so that it can activate the substrate and then gain back the electron. So this is something if you want to mimic, then you have to design some material which have the exact similar property, which can take electron, transfer electron, get back electron. So it could be electronic reservoir. Okay. So this is something we wanted to mimic the behavior of metal without using metal.
So why is it, sorry, a stupid question maybe, but why isn't then copper a good catalyst? Copper is
not a bad catalyst, by the way. There are many reactions can be done.
So almost any good conductor.
Well, I mean, I would not correlate directly to conductor, but I would say, as I told, this electron transfer and this energy matching is very important, right? So where this bond energy of Rx, it goes to antibonding orbital. The energy of the orbital and the palladium's energy of the electron, the transfer, this matching is very important. So in principle, any transition metal has the capacity. So that's why, let's say copper is good catalyst in one process, maybe that is not good for another process. But it happens so, the palladium is very good in forming CC coupling catalysis because it has got the right potential. Okay, right. So, in this slide, I'm trying to convince you, this is not something we have been trying to do. Okay, this is a very interesting review article came up in Nature, which talks about how can you do this metallic property, how can you implant in a main group elements, let's say. Okay, main group elements means, let's say, carbon 2 or silane, silicon, germanium. Can you use main group elements as transition metals? The proposal came something like that. It is possible to make main group elements like carbon 2, which is in low valent state, okay, not like normal carbon, which is tetravalent. Now, you can think about splitting hydrogen, right? Carbon 2, they showed in this paper actually, this is a paper actually, this is 2007. They showed that you don't need, for doing hydrogen splitting, you don't need any metal catalyst. Earlier it was all known hydrogenation has to be done through metal catalyst. But they showed in this paper that if you take a low valent main group elements, it can split the hydrogen, it can break the HH bond, but the problem is that it cannot do the catalysis. Okay, because why? Because I take you back to this cycle, it can do something like this. This is called oxidative addition. But once you are done oxidative addition, this is a carbon 4, it cannot go back to carbon 2. It's very, very irreversible process. So basically your cycle stops, okay, right? It's a halfway through. So, I mean, there was a lot of excitement. Even, I mean, last year, I mean, this excitement, many people believe that, you know, this is the way to go forward to mimic transition metals. But apparently there is no big, catalytic process came up, although other than fancy papers, okay. So this is something they tried to do nitrogen fixation without any transition metals. But the point I'm trying to tell you is that there are many people who are trying to avoid transition metals to do catalysis, okay, because of the same reason what I told you. Now, I'm introducing a molecule here. So this is, we call as phenalenyl or ply-based molecule, we call it as short PLY. You can think that this is if you consider graphene sheet, this is a 3 fused ring. And if you count the number of carbon atoms, there is 13 carbon atoms are there. It's got odd alternate hydrocarbon. And this is not a molecule, something we are introducing. This is a molecule which is known at least 60 years. Okay. So if we go back and see the history of this molecule, they are very well known in terms of material chemistry actually. So there are some key publications it's reported here. They are very good semiconductor, molecular magnet, bistable material. Even they have been reported as this RGB ground state, which is how Anderson proposed a long time back actually. So this is something was proposed, but nobody thought that this could be very interesting material for doing the transition metal mimicking catalysis or transition metal mimicking property. Why do you think so? Now I'll take you to the result of HMO calculation earlier. This is something back in 1950s actually. So this is a early paper came up in 1975, which talks about this molecular based on early HMO calculation that there are 3 electronic states they can exist as this molecule. One is neutral state where you are dealing with 13 pi electron because there are 13 carbon, just like benzene. When benzene is a 6 carbon hydrocarbon, right? Aromatic hydrocarbon, you have 6 pi electron, right? But this is a 13 aromatic hydrocarbon, so you deal with 13 pi electron in the neutral state, and this 13th electron will be unpaired, so it can exist as a radical in a non-bonding molecular orbital. What is the non-bonding molecular orbital? What is the advantage? Because non-bonding molecular orbitals, you can take out electron very easily, or you can put electron very easily without disturbing the molecule. Okay, unlike anti-bonding orbital. So this is a low energy orbital. So 13th electron will be unpaired, and this is called radical state. And this radical state is practiced over the years, like last 40 years, to do a lot of chemistry with this. Okay. Now you can easily take out 1 electron to get a cationic state, or you can put easily 1 electron to get an anionic state. So this is a perfect molecule which can behave like a metal, which can take electron or give up electron if you can design your reaction correctly. So that was our idea, that what we thought, we'll use this cationic state where there is no electron, and then we can actually make storage of electron and then transfer the electron just like metal to the organic reaction. Okay, so that was the idea we got started with. This is something, not just exactly catalytic, but this was kind of very enthusiastic result, which is in collaboration with my colleague at MIT actually, Jagdish Pudera. So when our initial results started coming, we saw that this molecule, when we put a metal center, this type of ply molecule, when you put a metal center, they're very good in accepting electron in solution. We have, cyclic voltammetric and all other studies. Then I was discussing with some of his collaborators that can you devise this whole electron transfer in the solid state or not? Okay, so that was the idea we came up with, and of course, this is something very successful experiment only I'm showing. We actually started a program where my student who started synthesizing a lot of molecules of like this, and then we figure out this is the successful molecule. When you put on a ferromagnet substrate, there is a solid state electron transfer to make this radical. So what is happening here, we are starting with this state, and then we are putting on a cobalt, is a ferromagnet, transfers electron, becomes radical in the solid state. And then when this measured in Mudera's group, when they measured the resistivity as a function of magnetic field, then it shows that there is a huge difference in resistance of one state actually. So if you change the magnetic field, the input electron, injected electron's magnetism changes and the resistivity also switches. So this was something, it was very, unprecedented result initially. And then what the control experiment shows, in between ferromagnet and this phenalenyl compound, if you put an inert layer like aluminum oxide there, then there is no such effect. So it was concluded that this is an interfacial effect, and this is because of some sort of spin filtration effect this is showing. Okay, so this is a cartoon video actually, which kind of explains that why this type of magnetoresistance effect. This molecule, when it sits over the cobalt substrate, it acts as a spin filter. So when the input electron is one type because of the magnetic field, then it gives one type of electron, whereas when it changes the input electron, injected electron's spin, then it gives another type of electron. Because of that, the resistivity difference is happening. Okay, so all these things I told because one thing we got sure, not only in solution but also in solid state, this molecule can capture electron and then they can exist in radical. So I think we have some 10 minutes time. Okay, so now, I'll take you through another 2-3 examples. H2O2 fuel cell, this is something used, H2O2 fuel cell is used for making energy, chemical energy to electrical energy. For example, Fukusumi from Osaka University dreams that so if you can convert H2O2 from air, then you can break H2O2 in a fuel cell and you can give the electrical energy. So you can even think about air-driven car. By the way, this is something fantasy, but what is more practical is that this H2O2 fuel cell is practically used in space station to give electrical energy or underwater application, because the alternative hydrogen fuel cell, you cannot take it, it's not so easy to carry because of the hydrogen storage problem, right? So now the cathode reaction, you can see the overall reaction is very green. You break H2O2 to water and oxygen, okay, and get energy. And then in the cathode, you use a catalyst which is based on platinum, right? Now what we thought, can we replace platinum with more cheaper iron-based catalyst? And then we used this type of catalyst to do whole fuel cell, H2O2-based fuel cell, and check the efficiency. What it shows, the efficiency of the iron-based catalyst is actually as good as platinum. And in fact, if you look at the cost difference between 1 kilogram platinum and 1 kilogram iron, you can understand how this could be interesting. Okay, so what we understood is that our molecule, if you start with, this can actually store 2 electrons in the system. One is iron 3 to iron 2, and the second electron is stored in the this organic backbone, and then you can take and break this 2 electron supply from this molecule, and the whole process becomes very efficient, as good as platinum. Now,
is the main obstacle to making this hydrogen peroxide fuel cell? Is it the platinum? Is it that?
So all is commercially available. It's not. I will not say obstacle. It is now in action with platinum.
But that's the expense.
Right. That's the expense. So it is already in reality. But we are trying to give idea actually how to cheaper metal like iron, because iron normally will not work unless you put our molecule which can help metal to store the electron and then supply 2 electrons together. Iron cannot give you 2 electrons together. Iron can give iron 3 to iron 2, it will go, and that can give you 1 electron supply. Okay, you need full reaction, you need 2 electrons. The second electron comes from the organic backbone actually, which can store the electron.
But so are you saying that now with this chemical of yours, you can make a more viable?
Right, once again, this is academic level, so theoretically I can say, but I did not make it. So, right.
The stability of the organic molecule, is that a problem, or
I'm sorry?
is the organic molecule stable?
This molecule, starting material is quite stable, yeah. Right, yeah, not a problem. But once it is radical, it is unstable. Yeah, you have to kind of, yeah. But we have seen the stability of this whole fuel cell. Recycling rate is good. 10 times we check. Now last topic which I started with, CC coupling catalysis without metal. That is something is very challenging, as I told that 2010 Nobel Prize was on palladium based catalyst. Now CC coupling without metal catalyst, how do you do that? Right. So there are some strategy I'll describe here, which is done with a stalwart like Gloria, Sanford. There are people actually across the globe. They are working. So what they did, they took one substrate and they took two catalysts. One is ruthenium iridium based and one is gold based catalyst. The one of the catalyst, what it does, it gets stimulated by light and then it transfer electron to aryl N2BF4 one substrate. And then another substrate is this one, then it gets activated by gold. So the point I'm trying to tell you is that there are two expensive catalysts was used for doing the reaction. One is gold, one is iridium based catalyst. One is stimulated by photon, it generates photo-generated electrons and transfer. And another substrate is activated by another gold catalyst. Okay. Now what we show here, unlike previous catalyst, what we show here, we can take a simple cation, our plication, which is having no electron, then we can use a chemical induction process. We can take a reducing agent which can transfer electron, load the electron of the in empty orbital, then becomes radical. As I told that radical's existence we have shown. Now this radical can transfer just like a photo-generated electron to this one substrate. And once it transfers, it comes to a cationic state which can act as a Lewis acid, like gold. Okay. And then do whole process of CC coupling where you don't have to use such expensive catalyst like orium or ruthenium or iridium. It's just a metal-free catalyst and do exactly same reaction, which is no metal is required to do CC coupling catalysis. Okay. So what we did with this help of this particular, so this is a very low loading of catalyst, 2.5 mole%, which is just like a metal. We could do metal-free catalyst and we could do CC coupling catalysis. We could show the application in gram scale of making a multi-billion-dollar molecule. BSF's molecule Boscalid, which is agrochemicals, and we have prepared in our method. We are using only palladium. So this is the first metal-free catalysis in CC coupling where we don't need to do any type of metal. How it works? If we go close. So the first step, as I told, you are taking an organic reducing agent and putting an electron on the orbital, which we talked about, cationic state. Now it becomes radical. Now this radical electron is transferred to the substrate. It breaks it apart to aryl radical, which is very, very reactive, and it becomes positive, means it becomes Lewis acidic. And this radical, of course, we could trap, and then another partner comes with the Lewis acidic state. So there is a dual role. One is electron transfer, one is Lewis acidic. Now another partner comes, goes close, then there is a CC bond formation between this, and then electron is back, and you get CC coupling part. So this is a whole new route how to avoid or mimic transition metals to do CC coupling. You know what I mean? So our catalyst is actually behaving like a chameleon, so where you can have a cationic state and radical state. They can switch back and forth, in equilibrium. Right, so this John, of course, globally good impact actually. This is somebody, I did not know I came out in the Chemistry World Journal, so he's a CEO of German pharma industry. So they think that this could be interesting for pharma industry actually. So he's from Germany and this is what it is. Now we also, as I told, that how to make industrially more viable. This is something I'm showing, that how to make the whole process heterogeneous. Okay, heterogeneous means you don't have to lose your catalyst. You can filter, once again start your cycle. So it's more cost effective. So use the graphene oxide surface to fix our catalyst and do whole process recyclable. Okay. So we did, so we did lot of chemistry, which is material science related, device physics, and then chemistry, catalysis, heterogeneous catalysis. Very recently, you also showed anti-tumor properties. So this molecule is marvelous, not only in materials but also catalysis, biology, and all these things you have shown. Just I'll take you a few minutes to show where we are heading for. So I did not tell what is negative, right? So I posed that everything I saw actually, which is not correct, right? So the way so far we are doing, we are loading an electron with our molecule by chemical reducing, that is a dot. Now we are transferring this electron to the substrate, okay? Then it breaks, creates a reactive species, then it combines with another partner to do the CC. That is the strategy we have used so far. This strategy is good for different types of bonds. Actually, I did not show, but there are very important bonds we can break, which is very important. But which we could not do, which typically a metal can do, in fact, aryl halide bond, which is quite cheaper. We could not do that activation so far. So, so this is the state of the art at this moment. This is the last year paper publication came. So if you take this CH bond and take a aryl halide, you can do this coupling with the metal at room temperature. This is the first report, room temperature. But you need two metals, palladium and silver, okay, to do this aryl halide and CH bond coupling, okay. Now this is known, this is called CH arylation. This CH you are taking and putting aryl group, this is called CH arylation. And this is at room temperature, first time reported a few months back. And people are trying hard to do this whole process without any transition metal, okay. This is just 1 month back science paper. They are trying without using transition metal, okay, palladium catalyst. They have done palladium catalyst, but this is not catalytic. This is a stoichiometric reaction. So this is more or less not so much valuable. Stoichiometric, so far this is the, so they could do this CH arylation. You see this CH, they put a aryl group across this here. This is this room they have put. The same process they could try, they tried with transition metal but stoichiometric but not catalytic. So what we are trying to do is that we are modifying our strategy. So far I talked about this is a mono-reduced species. Now we are going to increase the energy level of our active species by pushing another electron in this orbital to go for di-reduced species. So that so far as I told, if we put an electron to go to radical, it cannot transfer electron to aryl halide, okay, transfer electron aryl halide. You have to push your energy level higher by putting second electron to the orbital. Now you are putting second electron and then probably you can solve this problem. Okay, that is the way we are trying to go forward. With this, I must thank all support I received from my funding body, ICTS, Kolkata, ACRB, DST, and also a private company with whom we are developing a drug at Delhi. Actually, this is an anti-cancer drug for triple negative breast cancer, which I did not talk about today. We are very soon taking it for clinical trial. We have developed a molecule which will be which will undergo US clinical trial at so we just established the office in Princeton and then we'll go forward to that. So we got a lot of funding support from that company also, and my thanks to my collaborator as I named them earlier, and my students who have done all work with me. And thank you very much for your time.
Chemicals that you need to actually go through this process, are those difficult to make? PLY or other one?
No, it's not difficult to make because it's a simple organic reaction. We make it in gram scale, maybe sometimes 10 gram, 15 gram, we can do it. You need for a catalysis, in our scale of course, we need few milligrams, so it's not at all a problem. Even you can scale it up. So I myself did in 100 gram scale, so it's not a problem. Yeah. Only thing is I did not tell you is that I have to check something which I'm missing it. This molecule also I have to put it in tissue actually, so how they are bad to human body, because sometimes organic hydrocarbons are not so good for human body also. I started with the toxicity and also something. I have to figure out that. There's something is super pending. But synthesis wise is not a problem at all. It's very, very easy.
Regarding this question about energy, there's a lot of energy consumed in that process. Eventually you're getting for preparing this materials.
For the preparing this material, I did not do the head-to-head cost calculation. So energy and cost, both are, together. So I would say that if I do the cost calculation, I'm very, very sure that it's much, much more cheaper than palladium. Yeah, definitely. I did not have the number ready, but you can do that.
Maybe I have a question.
Sure.
Probably you have told us what is the main difficulty to do this reaction in industrial scale?
With our molecule? No, so I told previously, with this molecule, I am more confident. So there are two parts, right? So one is carbene part, one is this molecule. I am more confident that this molecule will be easier to take it to industry actually. Because this is scaling up is not a problem, but the other part, the stability is the issue actually. Okay. So any process we have to take it through, more or less take it through the heterogeneous process. So far, what we talked about all homogeneous. There are certain advantages of homogeneous and heterogeneous because I can understand mechanism easily. Heterogeneous, I can't do anything. Almost it's a black box actually. So because I cannot solubilize, I cannot see NMR, I cannot see anything. So always the catalytic design model starts with a homogeneous model and then goes for heterogeneous. The point I'm trying to give you answer in this way: heterogeneous genization of this particular compound is more easier than the previous one. So it is possible. I'm optimistic.
So let's have the speaker.